right, so everybody turn in their homework? Cool. Any questions on the homework? That's really good or really not good? Okay, we'll talk about the homework on Wednesday then, after I look at it. So we have 2 weeks left. We have a quiz on Friday, which will be like another, probably, I don't know if it's going to be 30 minutes or 50 minutes, but it'll be something. And what will the quiz be on? I don't know. What have we done since the last quiz? We did counting, pigeonhole principle, combinations, permutations. We started some graph theory, so it'll probably be some combination of that stuff. So we're going to finish up graph theory today or Wednesday, and then we're going to spend the rest of the course talking about formal languages, automata theory, state machines, theory of computation, Turing machines, incompleteness theorem, and we'll end with like the destruction of everything that we think we know about anything, which will be a good way to wrap up the course. So let's continue with graphs. So we put up some samples of graphs, cycles and wheels and complete graphs as things we could play with. And we finished by talking about a subgraph. So a subgraph is sort of the most intuitive definition. Take some collection of vertices and some corresponding collection of edges that make sense, you got a subgraph.
Can a subgraph be itself?
Yes, so everything's a subgraph of itself. And I guess, well, there's no empty graph because you got to have at least one vertex. But if here's a graph, right, then this is certainly an example of a subgraph. Right, because I've got a subset of, well, I've got all the vertices in this case, but I've got a subset of the edges. And this is a very particular subgraph of this original graph, because this is actually, if I think of this as a root, this is actually a tree. Right, where each node has descendants, and each of those descendants has descendants, and everything comes from some other node except for this thing we call the root, and nothing has two parent nodes, so there's no cycles anywhere. And this is actually something called a spanning tree, and it's a tree which sits inside this graph but touches every vertex, and we can get to every vertex from the root of this tree. And spanning trees are useful, for example, if you have a bunch of information organized as a graph and you want to somehow access each piece of information. If you can find a spanning tree, it gives you a way to get to every point from some starting point. And if we have weights associated with these, we can talk about a minimal spanning tree, which lets us get from one point to every point in the shortest possible distance. And there's lots of algorithms for doing all of these things, most of which we won't go into here. So some things we can do to graphs, we can remove edges. And to remove an edge, we just remove the edge. And that's all you have to do, because vertices don't need to be connected to anything. So if I remove this edge between B and C, I just take out that edge. And I've got the same set of vertices but fewer edges. And in fact, graphs don't have to have any edges at all. They have to have at least one vertex. But we can just remove edges freely and they just come out of the set. So if we have a graph G and we take away some edge E, where G was some set of vertices and edges, G minus E is the same set of, that's an ordered pair. G minus E is the same set of vertices, but it's the set of edges with that singleton set subtracted. So there's edge contraction. And edge contraction, we take out an edge, but then we take the two vertices that it was connected to and we join them. We turn them into a single vertex. So here's a graph. And let's say we want to contract this edge. So we're going to remove that edge, and A and C are going to become the same vertex. This is going to get ugly. So I'm just going to call this new vertex AC. So that gets connected to B, and that gets connected to B, and C is connected to E, and C is connected to D, and A is connected to D. So that would look like that.
Do the two parallel lines at that point like have a distinct difference? Or?
No, it's just two edges. So yeah, they are distinct. And we may or may not specify that we want a simple graph where we only have one edge connecting vertices, in which case that would just become a single edge. Okay, we can also remove a vertex. And when we remove a vertex, we remove all the edges that are incident to it. So again, here's a graph that seems to mean something to me. So if we want to remove vertex A, we get rid of A, we get rid of the edges that are incident to it, and we just end up with this.
And that's a subgraph too.
And that's a subgraph, because we haven't added any edges, we haven't added any vertices. All right, so representation of graphs. I should have done that in the corner because I need a graph. So here's a weird graph. And let me label the edges. We'll just label them W, X, Y, Z, and V, and U. So we have 5 vertices and we have 6 edges. Okay, so we talked about one way to represent this before, which was to make an adjacency matrix. So an adjacency matrix, we list our vertices. So adjacency matrix, and we basically use ones or zeros to say, are these two vertices adjacent to each other? So A is adjacent to B and C and E, and B is adjacent to C and D, and C is adjacent to A, B, and D, and D is adjacent to B and C, and E is adjacent to A. So barring mistakes, that's our adjacency matrix. And we can find some things in here. For example, if we want to know the total number of edges, how can we get that from this matrix?
Slice it diagonally and count the ones.
Slice it diagonally and count the ones, or just count all the ones and divide by 2. Same thing. Right, because every time there's an edge, there's a 1 in here that corresponds to it. We might have to be careful with loops, like B to B. Should count twice, but barring that. How can we find the degree of a vertex? Do you remember what degree means?
How many edges connect?
How many edges connect to it? So how can we find the degree of A from looking at this matrix.
Count the ones in A.
Count the ones in row A or column A. 1, 2, 3, that's the degree. Degree of C, 1, 2, 3. Degree of D, 1, 2. There's 2 edges connected to D. So there's a lot of information in here. Okay, so there's an alternate way, which is an incidence matrix. And in incidence matrix, we have our vertices in one direction, but then we list the edges in the other direction. And we show which edges are incident to which vertices. So A is incident to X, Y, and W, and nothing else. B is incident to U, V, and Y, and nothing else. C is incident to X, Z, and U. D is incident to just V and Z. And E is just incident to W. That's a different way to represent a graph. And pretty clear, none of these change based on how we actually draw this. If I had drawn E on top of A instead of below, that doesn't change anything in this, right? Because we're not concerned with geometrically where these things are sitting on a page. And these are convenient ways to store a graph inside a computer. If it's an unweighted graph and all we care about is connections between vertices or not connections, right? These are binary matrices, so every value is a 1 or a 0. If it's undirected, we don't need the lower half of this matrix, so we can use a triangular matrix. And binary triangular matrices, if you've done linear algebra, have nice properties. They're fairly easy to manipulate. There's some ways we can store them. And if we have lots of vertices and not too many edges, these tend to be sparse matrices. If you have 100 vertices, you could have a huge number of edges, right? Every vertex could be connected to every other vertex. You could have 100 to the 100th edges, but you probably don't, right? If this is roadways, 100 cities, how many roads do you have from one city to another? There's a few. So chances are most of this matrix might be a 0 in a lot of applications. In sparse matrices, we have ways of dealing with those in computers also. So there's a third way to represent graphs, and that's with an adjacency list. And how does this work? Well, we have vertex A, and we would say that connects to B, it also connects to C, it also connects to E. This is not saying that B connects to C connects to E, it's really just kind of a list, so let me draw this as like just commas. So B connects to A, C, and D. C connects to A, B, and D. D connects to B and C, and E connects to A. And so for each vertex, we can store this list of vertices that are adjacent to it. And so how could we store those in a computer? What kind of data structure might we use to store that list?
An array.
A what?
A linked list.
A linked list, or an array. Array, the only downside is we got to know how big it should be to begin with to declare it. But a linked list would let us grow indefinitely. So adjacency list usually stored as linked list. Each vertex is a pointer to a list, and it's just, right? Or, you know, we could have a linked list of vertices, and each element in that linked list of vertices could contain the identifier of the vertex and a pointer to a linked list of adjacent vertices. So different options depending on what kind of processing you want to do with the graph. And we'll hopefully get to Dijkstra's algorithm this class period, which is a way to find shortest paths through a graph. And you can think about some of these implementations. All right, let's revisit isomorphisms of graphs. So here's a graph. And we've kind of waved our hands at the idea that these two graphs are somehow the same. If we had these things with little connectors and pieces of string, we could turn this into that by just flipping these two things around, right? So we'd like to formalize this idea of isomorphism, which we sometimes write like that, an equal sign with a tilde on top. So here's a formal way of thinking about isomorphism. So two simple graphs. Simple means there's at most one edge between two vertices. So two simple graphs, G1 equals V1 E1, and G2, which is V2 E2, are isomorphic which we write as G1 isomorphic to G2, if and only if there exists a bijection, so a bijective function f from the set of vertices V1 to the set of vertices V2 such that A and B are adjacent in G1 if and only if f of A and f of B are adjacent in G2. This was easier with rubber bands and pieces of wood. And this is for all A and B in V1. Okay, what does all that translate to? It basically says if these graphs are isomorphic, we can find a way to map vertices from this graph to vertices in that graph. That's our function f. It has to be bijective, meaning it maps every point here to a distinct point over there. Every point over here gets mapped to by something, and different things map to different things. So one-to-one and onto, right, or injective and surjective. With the further property that if two things are adjacent here, the things we map them to are adjacent over there. And if we map to things that are adjacent, they must have come from things that are adjacent. So this map preserves adjacency. Okay, if you can find such a function, then you can say absolutely these two graphs are isomorphic. If no such function exists, they are not isomorphic. But if you can't find such a function, that doesn't mean they're not isomorphic. Maybe you just haven't looked hard enough. So you have to somehow prove that such a function does not exist, or find a function that satisfies that.
And to prove it doesn't exist could just be as easy as they're not adjacent on either one.
But for what function? For all functions, right?
Yeah.
So you got to somehow exhaustively show that no function you can come up with, right? And that's expensive, because we did a calculation before, how many functions are there from a set of n things to a set of n things, and it was a huge number. It's like n to the n or something scary like that. So these are isomorphic. Can we find a function that maps vertices to vertices? I don't know. Let's try it. So I'm going to do the hard part, which is just write down what we want. That's the easy part. So what should f of A map to? What should f of B map to? And so on. To come up with a mapping that preserves adjacency.
A to W, B to X.
Okay, let's map A to W. Let's map B to X. I like that so far.
C to Z, and D to Y.
What do you think?
So,
I think you nailed it. So A and B are adjacent, W and X adjacent. A and C are adjacent, W and Z adjacent. C and D, Z and Y adjacent, and B and D, X and Y also adjacent.
so I can say A mapped with S and B equal W.
So f of A equals X,
Yeah.
f of B equals W?
Yeah.
Okay.
So and switch C equal Y and D equal Z.
And D equals Z.
Yeah.
So AB, XW, BD, WZ, DC, WY, sorry, DC, YZ, and AC, XY. Yep, that's a good bingo too.
Does it work to think of it as though, like, you have kind of, the square is the shape that you want, and
Mhm.
you have this new graph over there, and you can manipulate that kind of through what we've done by mapping to specific variables. So,
Mhm.
like, for this instance, the first mapping would be as if they took Z and they twisted it.
Mhm. Yeah,
And
yeah.
For the other way, they just twisted X and
Yep.
Y.
So this mapping is actually showing us how to transform this into that, basically, right? So it is a transformation. So yeah, there's at least two functions that satisfy this requirement of a bijection that preserves adjacency. So those are definitely isomorphic.
Since we're like talking, we talked about like the matrices as well. Is there a requirement to these transformations? Like, do they only work if they're linear transformations?
They're definitely linear transformations, but I don't think that's sufficient.
Well, I was just thinking about like, you
Well-
were saying you'd have to start talking about how you could prove or disprove things.
Yeah, so you could prove that a function is not going to satisfy this by showing it's not a linear transformation, right? But what's happening when we say, let's take A and replace it with W, what's happening to the adjacency matrix?
We're swapping rows.
Yeah, we're swapping rows and we're swapping columns, which is like a linear algebra thing to do, right? And preserves certain properties. So yeah, so this is just, right? And it's basically just renaming. So the harder question is, you've got two graphs and you're not able to find a map like this. How do you know whether they're actually isomorphic or not? And that's a hard problem. And there's no good general solution for it. And I think that falls into the realm of what we're going to eventually call an NP-complete problem, which we'll do next week. And
Is there a more formulaic way to do it? So say that the two graphs were so complicated that when you looked at them, you couldn't, on your own, unravel it visually.
Mhm.
Is there a formulaic or?
you can write an algorithm pretty easily to do this. It's just it takes a really long time, right? So we could map A to, well, it can only map to four things, W, X, Y, or Z, right? And B can only map to four things, and C and D. And for each of those mappings, you check to see if it's a bijection, and if it is, you check the adjacency of all edges over here, all vertices over here, and see if it's preserved over there,
So it's like
right? But for n vertices, you got n possibilities here and here. It's an n to the
order
n
n
problem.
factorial.
It's worse than n factorial. It's actually n to the n.
N factorial is worse than n to the n, I think.
This is 100 multiplied by itself 100 times. 100 factorial is 100 times
Sure, I was
smaller
thinking of
things.
a constant to be n is smaller than
Right, right.
than a constant. Okay, yeah, that's worse.
Yeah. Now we can make it factorial because we know that a map from A to A is not reasonable. It's not going to be a bijection. So this could map to n things. This can only map to n minus 1 things, actually, because we're not going to map to the same thing that did. So we can actually bring it down to n factorial, but that's still really
Still
bad.
enormous.
Yeah. If you can find a polynomial time solution to this, you can rock the world. So we'll talk about NP completeness next week, and this will come up in that. But there's a series of problems that are really hard to find efficient solutions for. And if you can find an efficient solution to any one of them, it's been proven you can find an efficient solution to this whole slew of problems. And they're called NP-complete problems. And there's lots of graph theory problems, but there's also things like Mastermind and Battleship and a whole bunch of other games that fall into this category. And there's a really bad movie, it used to be on Amazon Prime, called NP Complete, I think. And it was about some mathematicians who crack this puzzle. And most of the movie, they're sitting in a room with a clock, and you just see the clock ticking, and it's like really tense, but actually not so exciting.
Solve the problem.
They did, but I forget what they did in the end. I think they like published it or something, but they were into some government site because they wanted to keep them quiet. It was kind of weird. All right, an easier thing to do sometimes, though, is to find some property of two graphs that tells you right away that they cannot be isomorphic. So this doesn't guarantee that two non-isomorphic graphs will fail one of these tests, but if these graphs fail these tests, you can say right away they're not isomorphic. So what would be an example of a property of graphs that we know right away these are not isomorphic?
Number of vertexes.
Number of vertices. Or the number of edges. If they have different number of vertices, you cannot find a bijection, right? Because if you have a bijective map from one set to another, they got to have the same number of things. If they have different number of edges, they can't preserve adjacency, because you got a different number of adjacent vertices over here versus over there. So these are examples of graph invariance. Properties of graphs that don't change under isomorphism.
Did the set of the degrees of all the vertexes?
Absolutely. If you look at the degree of each vertex, whatever the collection of degrees is over here, it's got to be the same as a collection of degrees on the other side. So invariant theory is a thing. We look at properties of things that have to be the same when we make certain changes to this thing. In this case, the change we're making is an isomorphic transformation, and these things cannot change under an isomorphism. So if you have two graphs where these things differ, you know there's no isomorphism. So if you're lucky, you can tell that right away. But it's usually harder than that. All right, let's talk about paths. And I have a big fancy mathematical description of a path that would fill half a page, but I'm not going to do that. Let's just go intuitively. So here's an example of a path from A to G. Bang, 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 bang. Right, so a path from one vertex to another is a collection of edges where the first edge connects our starting point to some other vertex, and the next edge connects that vertex to some other vertex, and so on until we get to an edge that connects one of our vertices to the terminal vertex that we're trying to reach. That gives us a path from A to G. But it's really just, you know, boing, 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 boing. There's a path. So it's a bunch of edges connected in the usual way.
So how would we write a path?
There's different ways you could do this. So for example, we could just say A, comma, B, comma, C, comma, F, comma, G to indicate the vertices that we travel through on our path. And we're still thinking of simple graphs, so we only have a single edge from one vertex to another. So if we just list the vertices along the path, that should be unique. Now, there's another path from A to G, which would be go from A to B to C to F and go back to C and go back to B and go back to C and go to F and go to G. But that's kind of a silly path. So we're not going to worry about paths like that. So there's some ambiguity in the terminology, but we're going to usually think of this as a simple path. So simple path, you're only using an edge at most once. And that's more interesting to us than paths where we can go backwards. A circuit is just a path that starts and ends at the same point. So if we start at A and we go to B and we go to E and we go to C and D and then back to A, that's an example of a circuit.
Would A to B to A be a circuit?
It wouldn't be simple though, because we'd be using that edge twice.
Okay.
But technically it would be a circuit. All right, we can talk about the length of a path, which is really just the number of edges. So this path from A to G, 1, 2, 3, 4 edges, so it has a length of 4. So mostly these are what you would sort of expect these terms to mean. That's usually the right thing. Now we may have directed graphs, in which case, there's a direction associated. And so here we might have, something from A to B and another path from B to A. And so here, A, B, C, F, G would no longer be a path from A to C because we can't go from F to G. The arrow is going the wrong way. You got to follow the direction, right? But we could go from A to B to C to E to G. That would be a path.
Is it still simple now that you have directed paths to go from A to B and then B to A since they're different paths?
So from A to B and back to A, I think that would count as a simple path, yeah. Bless you. So we're going to play with the Oracle of Bacon in 222 this week. But I checked the website and they actually have the data available for download. So there's the movie database, and it's easy to parse. So it's got a title and then the cast plus other stuff like producers and directors and so on. And this is 164,000 movies. So that's pretty good. And they apparently scrape Wikipedia once a month, pull down all the English pages and look for any reference to movies, and then they update this database.
This is to find the minimum amount of connections to get from one actor to Kevin Bacon.
Exactly, yeah. And the best number right now is 7. There was someone in the army in the 1800s who was in a newsreel with one other person, and that one other person was eventually in some other, early 1900s film with someone else. So it takes 7 links to get to Kevin Bacon.
By best, you mean the furthest, the most links?
Yeah. And my friend who is a super hardcore movie buff was really stumped to get someone higher than 3. So yeah, so connectivity. So we'll play with this in 222, but basically, you know, each movie becomes a node in a graph, and you create an edge between 2 movies if, each vertex is an actress or an actor, and you create an edge if they're in the same movie together. And so if this is Kevin Bacon over here, and this is Susan Sarandon, and we want to know what the connection is, what we're trying to do is find the shortest path from this vertex to that vertex. And any path, you know, will give you a link, but if you find the shortest one, that tells you what the Bacon number is in this case. And so we'll talk about shortest paths, but it's basically a breadth first search. If we start here and we find everything that's 1 link away, and then we find everything that's 2 links away and 3 links, as soon as we reach our destination, however many links it took, that's the shortest path. So you can do really important things with graph theory. Yeah?
Is that data available on the server?
Yeah. So just go to Oracle Bacon. On the side, they've got a compressed version of the data file I just showed you. And I think they have some code samples and all kinds of stuff, and there's some other oracles. So it's all like an open source project, which will probably be a 222 project at some point.
Yay.
Yay! Or maybe 223. That would be a good 223 project. We might do that.
Oh boy.
That would be cool.
That means we get to do that next
Yeah.
year, guys.
Yes, for instance, right, there are some actors that are like key actors to that, because they're connected to so many people. You can
Yeah.
almost always get to them in 1 or 2 steps.
Yeah, and if you have 2 Bacon numbers, you know those 2 people are connected by at worst the sum of those numbers, but probably something smaller.
But if you've ever just tried to play using your own memory,
Yeah,
there's
yeah.
some actors you can always go to.
Right.
You can always go to Samuel Jackson because he's connected to
Right.
thousands of people.
Yeah, and I'm horrible at those. Okay, so particular type of path is an Euler path. And an Euler path is a path that contains every edge. So
EULER.
yeah. So is there an Euler path through all of these vertices? Sure. We can go to B, and then up to C, and then come down to E, go up to B again, come down to D, and then go across here. So A, B, C, E, B, D, E. And we only used each edge once, and we managed to cover all the edges, starting from A. Now if I add something else down here, there's no longer an Euler path through here.
So just using 1 line.
Just using 1 line, basically, yeah.
Couldn't we do the same thing, but then the E would go to F?
Oh, you're right.
So we-
Yeah. Let me break it. There we go.
Oh no.
All right, that does not have an Euler path. That I can guarantee. Okay, an Euler circuit is Euler path. It's also a circuit, so it starts and ends at the same location. So let's look at some examples.
Wait, so for the first example,
Mm-hmm.
did the D need to go back to E to make it a Euler path? Because
Yeah.
it did, because didn't you already go to E once?
You can go to vertices more than once, you just can't travel an edge more than once.
Okay.
All right, so 3 different graphs, each with 5 vertices. So is there an Euler path through this first graph?
Yes.
So what would be a good path?
A, B, C, D, E, C, A. I guess that's an Euler circuit.
All right, so that's also an Euler circuit. Okay, how about this one? Is there an Euler path?
Yeah.
Yes.
A, B, C, A, D, no, D, E, C, no, never mind. That doesn't work.
There's A,
There
B, C, D,
is.
E.
You'd have to start
There
with.
A, B, C, D, E, you gotta pick up these edges too.
A, D,
You'd have to
C,
start
A.
with B.
A, D, C, A, B. Oh, no, I didn't do
Yeah,
it.
A, B, C, A, C,
There's a way to do it, I used to do it.
Oh, yeah. Not data didn't get it.
No, not that one.
So much harder when you can't actually do it.
I know, our brains aren't good at this.
Started something on A.
You can start anywhere you want.
So could you do C, B, E, oh, wait, no, it's so hard.
Caleb, you can do it.
Let me think about it.
You have to do it like any puzzle game where you just think of, you see it and you're like, oh, this is the way I would start it, and then you do
Yeah.
the opposite.
Right,
Because
right.
if it's a puzzle game, you can't do it the way you normally start it, because then there's no game.
Yeah. All right, so we'll do a 5-minute break. You can think about this, and then we'll talk about it.